When it comes to physics, I'm the best at mechanics. That's the stuff I feel like I'm really good at. Like, Tiger, do you think that I was better at teaching mechanics than electricity?
Yeah.
Yeah, it's just because that's the stuff I would like. That's my thing. That's what I really enjoy. That's like the engineering standpoint. But if you want to be an electrical engineer, this is the stuff you have to be good at. And I don't want to be an electrical engineer, but I was good. I mean, I can hang with the stuff. But I mean, the stuff that we have coming up, like I kind of feel like I understand a little bit better. All right, let's get this party started. Go.
What's up, guys?
What's going on, folks? All right. So I need to define for you guys. All right. So what we're talking about here is we're talking about electricity or the flow of electric charge. And when we there's we're gonna have to start this game off with a few definitions. All right. And I'm gonna probably bring it back to an analogy, and I'm gonna constantly bring it back to the same, to this analogy. But what we're talking about is the flow of electrons or the flow of charges. And when we talk about the flow of charges, that's actually talking about what electricity is. Now, if we have an actual wire and it's flowing through a wire, the charge is being carried and flowing through a metal wire, we measure things called the current. And it's the letter I. Got it? And how do we measure it? Well, it's actually delta Q over delta T. What do you think Q stands for? The charge. What about time? What about T? Stands for time, doesn't it? Yeah. All right, good. So what I'm talking about is how much charge has gone across over a unit time. That kind of makes me think of like a velocity or flow. Does that make sense? Are we cool?
Yeah.
All right. Now, how do we measure this thing? Well, we measure it in amps. There is both Tiger and Kalena, and I realize I don't have the chat up, so I can't see what Kalena is saying. So I'll pull up the chat so we can talk to Kalena as well. Because Kalena is important. All right. So are we cool with that? That's not like an equation I just pulled out of my butt. You guys understand where it comes from and everything, right? Like current is equal to charge over time. Now I have a question for you. When I say the word current, I'm talking about moving things. What does it kind of make you think of? Water. Water flowing. So the current could be a measurement of how well the water flows. What is that?
Traffic.
Yeah, traffic. Exactly, exactly. We're talking about movement, like a flowing. So let's talk about traffic. Let's make this. I'm going to change up this thing and make it the analogy about traffic. Actually, I might switch between traffic and water. But you guys understand, like, if I talk about, like, what is the current of traffic, I would say, well, how many cars pass? That would be the delta C, I guess. Delta cars divided by the delta time. The change in cars, how many cars pass divided by how long it took, and I can define a current based off of that. Are we cool with that? Does that kind of make sense to you? All right, cool. So let's talk about what causes that? What causes that flow to happen? Like, for example, if I had a I don't know, just like a tray with water in it. Got it? Would it flow?
Okay.
Would the water flow from one spot to another? Here's
No.
point A and here's point B? No, not really.
Just be like random.
It would just be a tray of water.
Yeah.
So, what would you do to make it flow, my friends?
You apply. Have something make waves or have a.
You're talking about what? Like throw a little kid in here and have him splash around? Oh, okay, there we go. Why don't we tilt it? Uh, what Vernon is suggesting is I have somehow change gravity to act on it. So I'm like, not Vernon, Victor. I'm sorry. So what are you talking about? Like use the force, Luke, and like make the thing change, or let's just change the direction of gravity. Why don't we just tilt the dang thing? All right? Because tilting it works just as well.
But that's only if we have gravity.
Yes, that is only if we have gravity. We're assuming we have gravity in this picture. Are we cool with that?
Okay.
In fact, Tiger could probably calculate out this inclined plane problem. But anyway, you don't even need to think about that. If I tilt it, what's going to happen to the water? It will flow, right? It will come over here and it'll flow in this direction. Are we cool? Well, that's kind of what you don't get. You can't have a bunch of charges on a wire and expect electricity to happen. Electricity is when the charges actually are moving. Well, that's the same kind of deal. If you just have charges on a wire, you just have a piece of wire and say, look, electricity. There's no electricity, right? So what do you need to do to put electricity in that wire? I need to put a battery on it. And that's kind of what a battery does. A battery pushes these charges along. Just like lifting up this thing right here.
It's a water wheel.
Will push that thing along. It will push that water along. Why? Why does this push the water along here? Well, because it has potential energy over here, and it has potential energy over here, but it has less over here than over here. And so there's a difference in potential energy, or difference in potential energy. And that potential difference, write that one down. Potential difference.
Oh, wait, there's a difference.
Yeah. But I mean, this is not a separate equation. I'm just kind of like talking now. This difference in potentials will give you movement, right?
Mm-hmm.
And if the potential difference is really big, what can you expect about the movement? Hence, if you have a 12-volt battery versus a 9-volt battery, the potential difference between a 12 volts is 12 volts. The potential difference between a 9-volt battery is 9 volts. Which one will move the electricity better? The 12-volt, the one that has a bigger potential difference. It's like tilting up your slip and slide even bigger. Does that make sense?
Yeah.
Yeah, we cool?
Yeah.
All right, cool. So we talked about electricity, we talked about movement of electrons. Now we're going to talk about resistance. And this dude named Ohm. Yeah. He's a German physicist. His name is George Ohm. O-H-M. So, here's how we measure the resistance. It's V equals IR. And this right here, my friends, is a super important equation. If you don't memorize any of the other equations I gave you before, don't worry about it. Memorize this one. This says voltage is equal to I. What does I stand for?
I, isn't it the current?
Current times what? Resistance. Does that make sense? The voltage is equal to the current times the resistance. Or you can even do this. R equals V over I. It's the same thing. And that's telling you that the resistance, how much resistance is in this thing, is equal to the difference of voltage, or this voltage that we have applied across, divided by the amount of current. Are we cool? So if a current is a really big number, if current is a big number, if the cars are flowing fast through this one area of the freeway, would you say the resistance is big or small?
Big.
If current is fast, if current is big, look at it mathematically. If the I in the denominator is big, what happens to the resistance?
It gets
Well, that totally makes sense to me. What's going on? Because what's going on is I'm saying that like, huh?
less. Do you want to
It
go?
makes WebExes better, I promise.
Okay. It totally makes sense to me. I'm not gonna do it now. Yeah, I know. All right. It totally makes sense to me because what it's saying is if your thing is flowing really well, that means there must not be very much resistance. Does that make sense? Like think about all right. So you're talking about traffic. If traffic is flowing really well, that must mean there's not much resistance in that area.
I was not like a there was like
No, the less toll booths there are, the faster. Vernon's coming up with an analogy and he's saying the more toll booths there are, the faster traffic can flow. That's not true at all because the toll booth. I'm sorry. Victor is talking. Victor is here. Victor is standing in front of me. And he's sitting in front of me, and he's saying that the more toll booths there are, the faster traffic can flow. And I disagree with that because at a toll booth, you got to stop, you got to pay the toll, and then you can go past. Why? Oh, I see what you're talking about. No. You're talking about something different, and I'll get to that later on today. It makes. I see what you're saying, and it makes sense. But what I'm talking about. Yeah, he mixed it up, and I'll tell you what. I understand what you're doing. We'll get there. But for now, I'm talking about voltage equals current times resistance. Do you understand this equation?
Yes.
And if I wanted to tell you, if I told you, here's the resistance, or calculate the resistance, you would say, well, what's the current and what's the voltage? And then you just say, okay, V equals IR, and you want to solve for R, you just say, okay, R equals V over I. V. That's what I said. All right, now, R is measured in what? Ohms. To represent that, we give it the Greek letter omega. So if you see something like that like it says, oh, this is 500 ohms, that's what it means. And that's the Greek letter omega. That's just the last letter in the Greek alphabet. Hence God saying, I am the Alpha and the Omega, the beginning and the end of the alphabet. He's more than just the end of the alphabet, but I'm just saying that's where that kind of comes from. All right. Now, an ohm is measured in what? Well, an ohm is actually measured in, what is another equivalent unit for an ohm? Well, it's actually volts per amp. How did I get that? Well, if resistance is equal to voltage over current, voltage is measured in volts, current is measured in amps, so I mean, ohms is equal to V over A, volts over amps. Yeah, this is the equation. This is the units. Does that make sense? Yeah, we're using this. We're running out of letters here, so we're using different same units and whatever. Yeah. All right. Now here's the hardcore definition, and I actually like this. I really agree with this. This equation, don't memorize. All right, I'm going to introduce it to you, and I'm going to show you what's going on, but don't memorize it. R is equal to rho L over A. Rho stands for resistivity. L is length, and A is area. I'm totally recording this. Yes, I think I am.
Oh, so you're only using
what? Yeah, I'm only using one computer for that. I hope so. Anyway, all right. Think of it like this, and I actually would probably do this. In fact, I kind of might. I'm going to show you guys what's going on. Let's talk about why does it have the L and the A, and then we'll talk about what resistivity is. Does that make sense? All right. Check this out. When I talk about resistivity of something, think of a resistor as if we have traffic here, okay? If we have a freeway, and this is a freeway, so here's your cars going on the freeway, and then all of a sudden your freeway goes like this. That would suck.
Oh, look at Hawaii.
Yeah, that would suck. But there's also a lot of parts of the road that look like Hawaii. So yes, the freeway actually does go like that sometimes. You guys ever notice what happens when it looks like that? Like, what would you expect to happen? I would expect to flow really nicely over here, right? And then what would happen if you add these jaggedy parts of the road?
Everyone has to slow down to make sense.
You're right. You got to slow down and make the turns. And let's pretend that it's raining on top of that.
People are trying to cut into lanes.
Yeah, they're cutting in lanes, those jerks. So essentially, your current is actually going to go down significantly because of the bumpy roads, right? Because of not the bumpy roads, but because of the plenty turns that you would have to make.
Yeah.
So all this is saying is your resistance will go up if the length of that resistance is bigger. Which one would suck more to travel on? This road up here or this road down here?
Which one would suck more?
Which one would suck more?
Are they the same length?
No, they're different lengths.
The one on the bottom.
This one's only like a mile long, and this one's like 10 miles long.
And it squeezes into one.
Let's make it 40 miles.
The bottom one would be worse.
Yeah, the bottom one would suck more,
Right?
right?
Again, you'd be able to drive on those distances.
No, you wouldn't. I mean, it would suck more. It would suck more to drive on the bottom one. So therefore, do you guys agree
But you
with
don't have
me
to turn
that
so
if I increase the length of my resistor, then your resistance goes up? Does that make sense?
Yeah.
If the jaggedy part of the
Yeah.
road go for a longer time, then your resistance overall goes up. Did you just break that thing?
Yeah.
I was going to save that for my kids.
Oh. Sorry. I'm sure we have more.
Thank you. All right. Well, let's break it all the way then. All right. All right. So you guys can hang with why the L is in the numerator for this equation. Because if L goes up, resistance goes up. Does that make sense? Why is the A in the denominator? What does that mean? How does that work with our analogy?
Because less area.
Less area? What does that mean? What? What are you talking about?
Less area.
Think about it like this. All right, think about it like this. By the way, I'll throw up the video camera as well. All right, so you ready? Wait, where's my video camera? There we go. Was your mom here?
Yeah.
Is she standing right over there? Did you wish her happy Valentine's?
Happy Valentine's.
Oh, happy Valentine's, Miss.
Yes, how are you doing?
We're doing good. In fact, I really enjoyed having Diamond here.
Thank you. Yes, she loves me.
Yeah. She talks so much to Brandy. All right. Anyway. So now we're gonna do this one. Okay, you ready? How does the area affect the resistance? Think about it. I want you to just sit and think about it. What does that mean?
Less resistance.
Okay, yes. Mathematically, I'm looking at this, and area is in the denominator. So therefore, the more area, less resistance. Why?
More space to flow.
Exactly. If we're talking about which one would suck more to drive on, this road right here, or this road right here. Wait for it. By the way, there's a bunch of dotted lines here. This is a 5-lane freeway that is curving up and down. I have no idea why you would do that, but I'm just saying. All right, whatever. There's the Statue of Liberty or something over here. Buildings or something, I don't know. So which one would suck more to drive on? The one on top or the one on the bottom?
The bottom is wider.
Yes, the one on the bottom is way wider.
One on the top.
This is talking about 10-lane freeway versus a 1-lane road. If you have more area, your resistance goes down. Does that make sense?
Yeah.
Yeah, it totally makes sense. All right. Now, what is resistivity? Okay, resistivity to me is dependent on the type of material. It's kind of like it's a
This
constant
right,
that we
right.
would have to give you just straight off. Like for example, what if we were traveling? What if we were traveling on the same road this time? Okay, we're using this one right here. Yeah, exactly. But instead of having asphalt for our freeway, we made it out of mud.
I wouldn't say dirt.
Yeah, dirt would be nicer. But we made it out of mud, just straight up mud. In fact, you know
That's
what?
not even a freeway. That's just like
Why don't we do this? Why don't we make this road out of tar? Okay, we just made it out of tar. It's like we thought we were gonna put a road there. We didn't put the asphalt down. We just put the tar.
artificial.
Which one would suck more to drive on?
tar?
The tar, right? Like the resistivity. If the resistivity is big, then your resistance is big. The tar has a high resistivity because it's sticky. It won't let you drive as well. Whereas if you're talking about like, okay, now we're gonna make it out of like brand new asphalt. No, we're not talking about like pothole version asphalt. We're talking about like brand new, just laid down asphalt. Concrete, fine. Talking about concrete. Which one would you rather drive on, my friend? I'd rather drive on the concrete. So that's what rho is. Rho is a measurement of the ability for the electrons to flow depending on the material that you have. So I have different resistivities. Let's take a look. The resistivity of quartz, fused quartz, is 7.5 times 10 to the 17th power. Does that mean that electrons can flow well through quartz?
Wait, what was it?
It's 7.5 times 10 to the 17th power.
No.
That sucks. That's a huge number.
Huge.
Yeah, electrons tend not to flow through quartz crystals, by the way. What about rubber? The resistivity is between 1 and 100 times 10 to the 13th power.
Nope.
Which kind of makes sense because if you're working with electricity and you wear rubber gloves, that kind of protects you because the electrons don't like flowing through rubber. The resistivity is too high.
But it's still possible.
It is possible.
You just need a lot of electricity.
Yes. So generally you're safe. You would be safer if you had quartz gloves. I don't think it's practical, but I'm just saying. Does that make sense? Or what about glass? How well does electricity flow through glass? It's between 1 and 100 times 10 to the 9th power. Not so good. All right, here. Okay. Let's look it up.
Resistivity of air.
Electric resistivity of air.
So apparently,
I don't even think they measure it.
the government didn't think I was a U.S. citizen.
What?
I changed my citizenship for my passport,
So therefore what?
and therefore Department of Justice did not work with Homeland Security and.
Were you born here?
No, I was not.
Oh, but you moved here a long time ago.
Yeah, I moved here a long time. I naturalized, but
So you're not a full-on US citizen.
no, technically I am.
All right, let's see.
We just don't have it on the record.
According to Wikipedia, how well does electricity travel through air? What is the resistivity of it? And it tells me. Yeah, do you guys think it's high or low? I'm just wondering.
I think it's high.
Actually, it doesn't tell me. Is this for air? No, this is just a general article on resistivity and
No,
conductivity.
just Control F.
Let's look up air. There's pairs, pairing, air. Good. 1.3 times 10 to the 16th power. Yeah, it doesn't flow very well through air. Okay, what would it flow well through? What do you think would be resistivity would be really low on?
Electrolytes.
Electrolytes. What do you mean electrolytes?
It's like ions.
Like what do we make our wiring out of? Copper, exactly. Why? Because
Salt.
copper's cheap. Copper is 1.68 times 10 to the negative 8 as far as resistivity goes. That's pretty small. We're good.
That was salt.
Salt. They don't have salt on here, but I'm sure that that you can look it up.
It's really low.
So, okay, well, let's look at this. What about silver? 1.59 times 10 to the negative 8. Dude, the resistivity of silver is better than the resistivity of copper. Why don't we make our stereo wiring, our electrical wiring, out of silver?
But we want it to be. Is it better? Is resistivity better or is
Resistivity is smaller.
Oh, it's smaller.
You got 1.68 times 10 to the negative 8 versus 1.59 times 10 to the negative 8. Which one would you rather make your house out of?
Because I'd rather not make my house out of silver.
Yeah. I think the cost of making your house out of silver wiring would be a little bit more expensive than you would want to pay.
Yeah, there's no really real benefit to it either.
Well, there is a benefit apparently. You get a difference of 0.00000001. No wait,
But how is
two
that,
more zeros and then 1
but how is that, how
resistivity.
How is that
Almost per
How is
meter.
that practically beneficial to you?
I guess if you're building a supercomputer or something like that, those kinds of things make a difference.
Well, if you build a supercomputer, you have enough funds.
Yes, if you're building a supercomputer and you're not trying to build a house
Gold.
out of stuff. Well, no, actually, gold has a resistivity of 2.2 times 10 to the negative 8.
Okay, how about
So I got a question for you now. They make super high-end stereos out of gold wiring, though. They use gold wiring.
because shiny.
Why would they use gold wire? It's not shiny because you don't see the wires. They cover it up with insulation.
Marketing gimmick.
This stereo is made out of gold.
Yeah.
No, why would they make stuff out of gold? Like even on like your high-end headphones, like
Sometimes they
Dr. Beats Audio or whatever, it has a gold-tipped
sometimes they don't
headphone.
want it to be as good.
Why?
They want it as much resistance.
No, that's not it. If the resistivity, if copper is actually cheaper and better, as far as like letting electrons go through it, then why would I make it out of gold? Can you guys figure out why?
So you don't want as much electrons.
No, that's not it. If that were the case, I'd use aluminum, which is actually even cheaper than copper.
Gold.
Can you think of it? Because it's gold. I could just say it's gold. No, here, I'll tell you why. Why do people wear gold wedding bands?
It's gold.
Because it's expensive. No. The reason why is because gold is a very non-reactive element. Right? Like if you have a pure copper statue and you leave it outside for a year,
AU, isn't it?
what is going to happen? You have a pure, nice, beautiful copper-colored statue, completely shined up. It's going to look
Statue
nice
of
and
Liberty.
copper. You leave it outside for a year.
Look at the Statue of Liberty.
What color is it going to be?
Green.
It's going to be green because it corrodes like that. What about if you leave a gold ring outside for a year? What color is it going to be?
Brown.
It's probably going to be brown from dirt, but once you wipe off the dirt, it's still going to be gold. You know what I mean?
How about silver?
Like that's why we wear gold, because gold doesn't react a whole lot.
How about silver?
That's why people who are like, I can't wear fake gold. I have to wear real gold. Well, the reason why they have to wear real gold is not because they're being like snobby. It's because the real gold doesn't react with their skin. You know, maybe their skin gives off a certain oil that doesn't react very well, and they're allergic to that. Well, the real gold won't do that. The real gold doesn't, like it has the right amount of electrons that it doesn't want to react with that. That's a chemistry thing.
How about silver?
Silver as well. Silver doesn't really react very well with a bunch of stuff. So gold and silver, that's why they're the precious metals. Because like they don't react well with others. Yeah, platinum and diamond also don't react. Actually diamond does react, but it's carbon. Carbon is a very solid thing. I mean, it's just like solidly built. So you guys, do you guys see what we're going on here? Do you guys see why I'm talking? I mean, like all of this stuff. We cool with this?
Resistance.
Yeah. So I mean, does this make sense to you? Like, I didn't pull this equation out of my butt. It makes sense, right? Resistance is equal to resistivity times L over A.
Yeah.
Now I spent all this time discussing that with you, and then I'm telling you now right off the bat, don't memorize that. No, I want you to know it. But what's really cool about this is this.
Don't memorize. I want you to know it, but don't memorize.
Well, see, don't. If you, I want you to memorize V equals IR because that's an important one that you are constantly going to use. For resistivity, there's very few problems where you actually have to think about resistivity. But I want you to be able to know it like you've seen it before. And then when you're asked to do a problem like that, like, oh, I can go look up that equation. You see what I mean? There's certain equations that I want you to know just because I want to introduce them to you. There's certain equations I want you to know because you're going to have to use it for the next 50 years of your life. No, there's not so many equations, really. Like even this equation, resistance equals resistance times L over A. Is that really an equation you have to memorize, or can you kind of think your way through that
You
one?
can think your way through it.
Like you can kind of build this equation without actually knowing it. You just be like, it's about here. Oh, fine. Don't memorize Don't memorize this equation. Just logic your way through it. How's that?
Logic.
All right, cool. Moving on.
They use such like they use the same letters.
Oh,
Science.
temperature dependence on temperature dependence. Let's talk about that. Your resistance, and this isn't in the equation, but it could be. The resistance depends on temperature as well. Why is that? Can you think of it?
Because it changes the material.
All right.
Resistivity.
Well, here I have a question. What is that? I have a question. Yeah, I don't know. Here, wait, Kalena, am I making sense here? I know that you're sick. I just want to get your heads up. Kalena? All right. And then Tiger, am I making sense? Because I'm kind of talking about this, but I think I'm trying to explain this in a way that I think it makes sense. Tiger?
Yeah.
All right, cool. All right, so check this out. Think about this. Because I actually did this. I said, all right, I used to teach community college, and I actually was talking to this guy on the bus that I taught community college to. He's now an engineer. He's making more money than me. I'm real pissed about that. But anyway, when I was teaching him physics, I did this. I said, all right, here you are, and you're standing over there. Got it? Actually, let's make him red. All right, so you're red, and you're standing over there. You got sunburned, whatever. And you want to walk through this hallway. You want to get through this hallway as fast as you can. So you start running to the left. Got it?
Yeah.
Now, if there's a lot of twists and turns in this hallway, what does that do to your ability to get through this thing?
It forces me to think.
Well, I mean, it just slows you down, really.
Yes.
So you're not going to travel as fast, so therefore your resistance actually went up.
Yeah.
Right? And then we can even apply this analogy to, like, fine, let's make the hallway smaller. If this hallway were smaller, how would that affect your ability to run through it? By the way, there's people in this hallway as well.
It'd be more difficult.
It'd be even more difficult. Your resistance is smaller. Therefore, remember we were talking about how area affects it. Cool? Now, I'm telling you temperature affects it. When I talk about temperature, and you talk about like a gas or something like that, if I heat up a gas, and this is kind of a chemistry thing, what is the molecules of the gas going to do when I heat up the gas?
They're going to go crazy.
They bounce off the walls even faster. Right? Does that make sense? They just like bounce faster. Okay? Now imagine this. Imagine that you are you're trying to get through this hallway, and you got a bunch of people in this room, say 10 people in this room, and they're bouncing off the walls. Like they're a full-on mosh pit mode. Like we're talking about like a band, a rock band. Let's do Kiss. We got Kiss playing rock music, and you got like people in a mosh pit. And you need to get from this place to another to get a message to your friend. How is that going to affect your ability to do that? You don't need to hear. I'm talking about running across this hallway. Not necessarily. No, you wouldn't, because there's 10 people in this room. This time they're running around though. Right? You would bump into a lot more people. I agree. So there, how does that affect your ability to get through this hallway? Does it make it easier or harder? That's what my question is. I'm gonna ask Kalena. Kalena, does it make it easier or harder to get through this hallway?
Why is Kiss playing with the hallway?
Because they're kids and they can do whatever they want. Fine, let's make it Journey.
Who played?
Journey does. All right, so we got Journey playing, and they're playing. No, it can't be Journey. Journey doesn't play like. You don't like do a mosh pit to Don't Stop Believing. All right, it's Kiss. I'm sorry. All right, fine, Metallica. So you got Metallica playing in a hallway. Apparently, you got like 10 people there, and they're bouncing off the walls. How is this going to affect your ability to get through the hallway? Kalena, come on, answer me this question, please. If you don't know, just say IDK, but I just want to make sure you're listening. I don't think she's listening, or I don't think she can hear. Or there we go. I was listening, and I don't know. All right, fine. Tiger, what's your thoughts?
Well, if they bounce all over the place, wouldn't that make it harder to move?
Exactly. If they're bouncing all over the place, I would go through and I would like be knocked down a couple of times. I'm sure of it. I mean, it's Metallica, and we're talking about like 10 crazy headbangers, right? So, as the temperature goes up, what would you say about the resistance?
Oh, that's what.
This is what I mean.
But isn't the resistance in a wire? Isn't everything in a wire still like solid?
No, because you still have atoms inside of that wire. Those atoms will move around. You're right. A wire doesn't have gas molecules that bounce all over the place, but they do move and vibrate,
Wow.
right? And we're getting down to that idea, that level.
It's basically like walking through a hallway.
Yeah, it's harder to walk through a hallway in an earthquake because it's hotter because the atoms are moving around and it's harder for you to get through there. So as the temperature goes up, your resistance does what?
Walking through a ship on stormy waves.
No, I want you to say up or down.
Oh.
As your temperature goes up, your resistance
Up.
goes up. All right? Now, let's switch out Metallica. Sorry, Metallica. You got replaced with Kenny G. Do you guys know who Kenny G is? He's the saxophone player to the
Snickers
Lakers.
commercial. I saw him on the Snickers
Right?
commercial.
And then when people listen to them, they're not like Metallica. Like Metallica's like, Earth in light, right? Or that kind of stuff. Kenny G is like when you listen to Kenny G, it's kind of like this. Or at least that's what I do. I'm not rocking out to Kenny G. So, we got our people here, and what did they do? Well, same amount of people. But this time they fell asleep. It was like,
Oh, that's sweet.
or yeah, okay, fine. They're swaying just a little bit, ever so gently. And you're over here, and you got to get through this thing. How are you doing with that? Can you run through, or you can get knocked down?
Yeah, I know.
You can run through as long as you're not swayed by the sweet sounds of Kenny G.
I was gonna say we're on a ship.
Yeah, you can run through. Okay, fine. You can run through. You'll be fine. And actually, why do they cool down computers? Why do computers not run as well when it gets hot?
Oh, because the processors can melt.
No, it's not that. Well, yeah, you could burn out the processor and what, but why do we cool down computers?
We want to make sure that they run to optimal levels of performance.
Well, why? What's the point of? I mean, how does it help by cooling it down?
The hotter it runs.
The hotter it runs,
Resistance.
the more resistance. Exactly.
Information has.
The less, the cooler it is, the faster this information can get through. The easier, the less resistance it goes.
That's why you have like 2-inch thick pipes and cracks coated.
Yeah. Does this make sense to you? Like, I mean, That's why. It's because it decreases the resistivity, and you can get your information through without having all of these roadblocks in the way. So here's one thing that's really interesting. Like, if you want to make a really, really, really fast computer, what would I do to the wires?
Put them in liquid nitrogen.
I would put them in liquid nitrogen. Why?
They've actually done that.
Yes, they have.
Should have seen the.
Yes, and it works really fast. You would cool it down really incredibly low. In fact, because very cold means low resistance. And that means your computer can even operate faster. And that's a good thing. Now, how low can we go? Do you guys know?
Minus
So-
273.
All right.
273 is absolute zero, right? Minus 273.
We can go to 0 degrees Kelvin. And well, actually we can't. It's theoretically impossible to reach 0 degrees Kelvin, which is called absolute zero. But we can get pretty darn close. What's really crazy is we can actually create these things called superconductors. So we have conductors which has a very low resistivity. If we can decrease their temperature to below 4 degrees Kelvin, we can make superconductors. And that's where electrons flow so fast that you're building quantum computers. In fact, and here's the crazy thing, and this actually happens, I've seen this done at a TED Talk, is when you cool it down that low, then things start to float.
Oh yeah, I saw that.
Like it just straight up floats. And it's really because yeah.
Because it was
And that has to do with this thing called the quantum effect, which is a level of physics that is a little bit above you. In fact, I actually don't understand the math of it just yet.
a quantum computer can do several things at once.
A quantum computer, if we can build quantum computers, we can build we can do a lot of things. Yeah, there's a lot of things we can do. Yeah, it's like the picture on the left. Go look it up. TED Talks absolute zero or close to absolute zero. Are we cool? All right. I feel like we talked a lot about a bunch of things. Let me see. What's coming up? I should probably do a few example problems for you. Why don't we just finish talking about this? I want you to read this chapter 21, because I think it's really good. But let's kind of spend the last 10 minutes talking about the toll booths that what you call it was talking about, that Victor was talking about. All right, here.
Hi, my name's what you call it.
His name is usually Vernon.
Yeah, usually.
All right. Oh, whatchamacallit is better than Vernon, your brother? All right, fine. So you guys understand resistance in this idea, right?
Yeah.
Now, in an electric circuit, what I'll usually have is I'll have this kind of stuff. I'll have a wire, okay? And I'll have a battery, and we usually make the battery look like this. There's a big line and a small line. Got it? By the way, do you guys know what this is? If I draw this, I'm just curious to know if you guys know what this is. Right here. I'll show it to you. Ready?
It's a capacitor.
That is a capacitor, my friends. Yeah, we did. We went over this once before. All right, but here's what a resistor looks like. Hey, doesn't that look like our analogy? Yeah, that's actually how they diagram resistors. They just put a little bunch of squiggly lines in your wire. And then we know, hey, there's a resistor there. Got it? So I got a wire with a resistor. In fact, I just described a light bulb. This, my friend, is a light bulb.
So what does a resistor do?
Well, a resistor causes like a disruptance. But I guess that's a great question.
Why would you want disruptance?
Why the heck would you want a disruptance in your wire? Well, It's because when you have a disruptance, you can this disruptance, the amount of disruptance, and this is the part I skipped, so I guess I shouldn't have skipped it, is related to a power output, and it's P equals IV. P equals IV.
Piv.
PIV, exactly. Power equals IV. And so if you have a
Power in
resistance,
joules.
all right. So we also know Ver, right?
Power in joules.
Power in power in watts, actually.
Watts.
Yeah, like a
Oh,
100
watts,
watt
yeah.
light bulb and 60-watt light bulb, measuring power in watts this time. So energy is in joules, power is in watts. But anyway, so essentially we replace this V with that V, and we have P equals I squared R. I times IR. All right. Also, I mean, an equation that you should probably know, but not necessarily memorize. And so, what happens is when we have a resistance in a wire, it will actually cause, like that's how we can get a light bulb to light up, is we have a resistance. In fact, if you look inside of a light bulb, what are you going to see? Like we're talking about old school light bulbs. We're not talking about the new curly looking ones. You're going to see this. You're going to see a big wire, and then you're going to see a small, tiny wire like this with a bunch of curls in it. All right, fine. Here, are you guys ready? When I plug in this light bulb, it's going to give off light. Why did the wire in the middle get super tiny? Like the size of a hair? Why do you think? No, it's not so much. I mean, yes, it does get hot, and we'll talk about why that happens. But why did I go from two larger size wires to a small little hair-like wire in the middle?
Is it a resistor?
It is a resistor, so therefore, when I made a smaller wire, what did I do?
Are we talking making it by putting electric current, or making it and then just
Like I'm talking about, why is the inside of a light bulb have a smaller wire all the time? Why is it a super thin wire? Yes, because we don't want as much electricity to flow through it. When we don't want as much electricity to flow through it, or we want to restrict the current, that's called adding. So it's with an R. Resistance, exactly. But what does the small wire have to do with it?
it reacts to the gas around it,
No.
causes light.
Think about this. Which one would an electron find it harder to travel through? The big wire or the small wire? The small wire is harder to travel through, so therefore it's increasing the resistance. That's why you get a brighter light bulb the smaller you can get that wire inside. Because it decreases it increases the resistance, or it decreases the area that we're talking about.
So we have a more concentrated flow.
So the flow of the electron is more resisted, and therefore your light bulb gets brighter. Why does it get brighter, and why does it get hotter as well? It's because the electrons are actually crashing into the atoms of the wire. And the smaller the wire, the harder it is to get through. That's like what we're talking about. When we make that hallway small and we keep the same amount of people inside, it's harder to get through. The resistance is going to increase, and it's going to get hotter because each time you run into somebody, they're going to get pissed.
So like speed skating, that's really it.
I guess speed skating. All these analogies kind of work. You guys understand what's going on? All right. Well, next time we talk, I'm going to talk about how to add resistors in series and parallel, and I'll tell you what that means later on.
Other than light bulbs, what do you use for?
Resistors is pretty much it's a combination of resistors and capacitors that pretty much make up everything in our electric. It makes up everything in our electronics. Everything that is electronics is pretty much just a combination of resistors, capacitors, and these things called transistors. That's it. You want to be an electrical engineer? Resistors, capacitors, and transistors. And how to add them, how to subtract them, how to combine them in a special way to make things happen. You make buku plenty money. In fact, I knew a guy who designed transistors, and to be honest with you, like I've done the math with them, it's super, super complicated. But anyway, I knew this guy, and he would work maybe 3 weeks out of the year. They would call him in. He would design a resistor. He'd make 100 grand in that 3 weeks, and then go home, and that's it. And just party like it's 1999, and then come in the next 3 weeks and work. That's what he did. Yes. Actually, he did other things besides just design resistors. He made more money than that. But I mean, like, if he wanted to, he could have just kind of like, dude, I'm not gonna work. I'm only gonna work 3 weeks. Okay? I'm gonna come in, design these transistors, because he understood, like, he understands physics way better than I do. Anyway. Yeah, well, you really got to be kind of a genius to do those kinds of things. There's not a whole lot of people who can do that, but the people who can, they make bucks, man. Anyway, yeah. But what was cool about it is like he didn't actually make a super amount of money all the time. He really did only work those 3 years, and then everything else he did work. He just did it for fun. He was like, I'm gonna volunteer at a camp. I'd be a camp counselor for 6 months. And he did that. Why? Because it's fun. Did he make any money doing that? Probably a couple bucks. You know? But, like, I'm going to be a waiter. And he would just pick up jobs just because he made all the money he needed to live on in 3 weeks. Anyway, I'm done with class. I got my 5 minutes left, but I wanted to kind of release your brains. I need to put up chapter 20 homework, and I need to start working on chapter 21. And I think that this stuff is going to be more fun for you. Hopefully. How did you folks feel about this new topic?
Less stressful.
What about you, Tiger?
I like it more.
Yeah, it's something to think about.
It's easier to wrap your head.
Yeah. Yeah. And actually, this applies directly to like pretty much all these things. Like, I think the easiest one to think about, though, that we're going to start talking about is the old school Christmas lights. Yeah, the ones that when you pull one out, then the whole thing just kind of like craps out. Like the whole strand sucks because one.
Strand of 100.
Yeah. So you know what? We're going to talk about old school and new school Christmas lights. Like, why did it used to be that when you pull out one, the whole strand dies, and now when you pull out one, only a third dies. Yeah, only a few of them die. We're going to really get into that because I think it's really interesting.
Parallel and series.
Anyway, hey, Kalena, where's your brother?
He's probably stuck in traffic.
Maybe.
I don't know. I asked him where he was like yesterday, and he was like, "Oh, traffic with that."
All right. Anyway, I'll talk to you guys later. Have fun. See ya. He's on the bus, but he left late. Yeah, it's cool. All right.
Stay with the bus. You have to catch it on time. Otherwise, you're kind of.
Yeah. You have to be on time, otherwise you're late. Great deduction.
No, I mean like the bus will leave without you. It's to wait for the next one.
I know. I hate that.
Half an hour. It's like.
I know. Sometimes the worst part is when you like walk outside and you see the bus pass by.
Oh, yeah. No, one of the worst things is like you almost get to the bus stop, but then it just passes by you. You're just scrambling to get there so they can see you before it passes by. Because like when there's no people at the stop, they just drive by.
I know.